Okay, so now you will see why this Bethe approximation is beautiful and we love it. So, and we want to understand the loopy belief propagation, which is kind of mysterious. And you will see that we can just writing mathematics, using mathematics, we can show you that all these math messages have a real meaning. And Nicholas Rossi is an amazing scholar. Also Eric Schenk, he is great at teaching these concepts of Bethe approximation. I have learned many things from his papers, books, slides. He's really nice. And so these are really important articles if you want to understand the connection between max product and message passing and Bethe approximation. So the time complexes of junction tree that you use to overcome the problem of loopy graphs is that the problem is that the junction tree has high computational complexity. So what should we do? Algorithms like message passing perform well on tree-structured graphs. When we have loops, we should use that junction tree and then say now that it is tree, then we can use the exact belief propagation. So we turn it to somehow tree-like. But let's review belief propagation. You will see that this is the message that goes from node I to J. And if you multiply these kind of messages and multiply it by your potential, you can get the marginals of any node that you want. And this is the loopy belief propagation. So to understand that, this P is difficult, okay? But we approximate it by Q using the KL divergence. Of course, KL divergence is not a distance. Even the symmetric version of that is not a distance. But, it's easy to work with these. That's why in machine learning we work with KL divergence, although we know it's not a distance. So we want to minimize this. When Q goes to P, this becomes 1. The log becomes 0. KL is minimized. It's 0. So I don't say distance. I mean their difference is low. And so let's approximate it by Q. You can write the KL divergence as minus entropy and this expectation of log term. But we know what is probability of X. We know that it is multiplications of potentials and then marginalize it. We know that. But Z comes to the denominator, and so it goes like this. But we can ignore for now. We can minimize this Gibbs. We call this Gibbs free energy because it's very important. So Gibbs free energy, we want to minimize this Gibbs free energy. So for that, the probability distribution, assume that we have a tree. And these are, for example, your factors, one factor, the other factor. We approximate it like that. So this term is for these variables that are at the end, to just have one edge. And these terms are for the rest of the nodes, like these. And this is the probability distribution of a tree. You see, it's very simple. And for that, the entropy of that becomes very simple. Entropy of a tree. And if you write that, you will see that the Gibbs free energy, the free energy of a tree becomes very simple. But if you write the Bethe free energy, Bethe free energy, we know that it's just an approximation because We just leave it down. We just leave it. Because we still don't know B, but we will learn it. And this is the Bethe cluster graphs. So how can we learn it? It should satisfy the constraints that they sum to 1, any probability distribution. And also it should satisfy the marginal things that we need in any probability distribution. And because we want to learn your B's, these B functions, then we differentiate with respect to those things that we don't know. And it achieves your general form of B. And now what if lambda is just the messages? That's the idea of this one. That what if your multipliers, your dual variables, are just the messages, the log of messages? Then you will see how these messages are related to these Lagrangian multipliers, these dual variables. And that's why this is interesting. So now you understand what are these messages, or what are these dual variables. Dual variables are just the messages, because if you write it, I don't have here, but if you write it, you will see that they are the same equations. Therefore, the doubleton and singular potentials in the Bethe approximation problem can be interpreted as beliefs at each iteration of loopy belief propagation. Moreover, the analysis shows that the belief propagation on factor graphs is equivalent to minimizing the Bethe energy function. Similarly, the loopy belief propagation algorithm would converge to true values in case of tree-structured graphs and may only approximate the true values in case of general graphs. So this is the general theory of loopy belief propagation. As I said, we just need that Q to approximate that, to reduce that KL divergence. Then we saw KL divergence. If we ignore the Z term, it becomes the free energy, and we can approximate it by this B. And of course, the feasible set, it should satisfy these probability constraints, And this is like a iteration. The loopy belief propagation has a fixed points. It goes and then it's like a dynamical system. It goes and converges to something. But when it converges, the solution it minimizes that free energy. And you will see here. First of all, mean field approximation, you know that you can multiply your Q's. It's very simple technique in variational inference, but this is important. We wanted to minimize the free energy that was negative entropy and this. But we had some constraints that Q should be like mean field as a mean field approximation, and also should be a distribution. You cannot take any function, it should be a distribution. So we can approximate this H here by linear sum of, by the sum of HQ, Xi. And also you can approximate expectation of log of F by this, because this is the mean field approximation of Q. And now you can write everything like this. This is your Lagrangian.